All right. So this next section will largely be talking about one-dimensional geometries. One-dimensional geometry is the best intuition I can give you for what we'll be talking about now, or what we call analytic geometry in one dimension. So let's talk a little bit about analytical geometry, or analytic geometry. I assume the majority of you have taken just a regular geometry class, right? You've done some basic geometry. And you might notice that when you're dealing with basic geometric figures, you don't really use numbers. When you're dealing with just some random triangle, for example, and you know that this has point A, this has point B, and this has point C, the notion of those points having coordinates isn't something you use in geometry. You don't talk about the coordinates of A or the coordinates of B or the coordinates of C. It's not a thing in just plain geometry. And so regular Euclidean geometry is developed this way with no notion of numbers when you're doing regular Euclidean geometry. Analytic geometry is the attempt to combine planar geometry with numbers. That's what analytic geometry tries to do. So, famous mathematician by the name of René Descartes. You've probably heard about him a bit. You hear anything about René Descartes? You know nothing about him?
Doesn't he have like a roll?
Have a what?
A roll of math
A roll of math?
with algebra? I
Like
guess
a
if
dinner
he's a
roll?
mathematician, never mind, keep going.
So a lot of people also know him a little bit for his philosophy. One of his most famous one-liners is, "I think, therefore I am," René Descartes. Well, he was also a great mathematician, and he had incredibly poor health. And so he spent a lot of time during the day sleeping, and didn't have a lot of time to spend working on mathematics. And he found the Euclidean geometry developed by Euclid, what was done in Euclid's Elements, to be very tedious. And he lamented how, with many of these proofs, you had to come up with some clever way of thinking about the problem to come up with your proof. Drove him nuts, he hated it. So he had this great idea: what if I just take my geometric figures and draw them on some coordinate plane like this? And so this coordinate system that we typically use when I talk about the coordinate plane, we call the Cartesian coordinate plane. Cartesian is coming from his last name, René Descartes. So, in a weird way, it's named after him. So the Cartesian coordinate plane, it gets its name from René Descartes. And that was his, essentially his big idea is, what happens if I associate to each point here a set of numbers over here? And that's how we create the Cartesian coordinate plane. Now we'll have a lot more to say about this in the next chapter, about two-dimensionals. We're now going to reduce this conversation from here on out to a one-dimensional conversation. And rather than talk about a coordinate plane, we're just going to talk about one single line. That's what I mean by one-dimensional. With me so far? Mm-hmm. Okay. So first section we then talk about, well, second section in this chapter, is about directed line segments. Directed line segments. So let's start out first off with a directed line. So a line L is said to be directed provided one direction is considered positive and the other direction is considered negative. So I draw some line L here. I signify this end over here, I'm going to call the negative end. I signify this end over here, I'm going to call the positive end, or positive direction and negative direction. And this is now a directed line. Good? Pretty straightforward? Mm-hmm. Pick 2 points on that line, AB. Now I have a line segment. And now my line segment has a positive direction and negative direction, same as a line. And so now this is a directed line segment. So a directed line segment is a segment of a directed line. Pretty straightforward? Mm-hmm. Okay. So now we have a notion, or notation for talking about the directed distance of a directed line segment. So when you see AB here, so first off, we just talk about the line segment AB. Here's how we would talk about the line segment AB. That's how we signify it, and you probably did that all the time in your geometry class. But in your geometry class, when you want to talk about the length of AB, the common notation that you used was just a line like that, right? And this was the length of AB, but AB was just a line segment. It was just a segment of a line. A line in regular geometry has no notion of direction, positive or negative direction. It's just a line. So when we talk about now a segment of a directed line, this AB now, with a line above it, is a directed distance rather than just a distance. Meaning it can now be positive or negative. It's no longer just the length. So when I write AB with a line above it like this, notice that B is on the positive side, so we're going from A to B in the positive direction. This is a directed distance from A to B, and it's going to be a positive number. If I write the B to A, the directed distance of B to A, this segment, notice from B to A, now that's going in the negative direction. So that's going to be the negative of the distance you got going from A to B. You with me? So if this distance were 2, from here to here were 2, then AB with a line above it would be positive 2, BA with a line above it would be negative 2, because it's going in the negative direction. And so the length of the segment AB now, when we're talking about a directed line, is the absolute value of its directed length. Always and forever. Regardless if this comes out positive or negative, absolute value always makes it back to positive. Right? Yeah. And let's note something here. I'll erase my answer. When we're talking about directed distances, the directed distance from A to B plus the directed distance from B to A is always equal to 0. The directed distance from A to B is going from here to here. The directed distance from B to A is going from here to here. And so when it's all said and done, I went from here to here. How far did I go? 0.
Yeah.
Ponder that for a bit. Okay, so I think you got some pretty good intuition for a directed line segment, right? Now, something I wish we were proving, but the author just noted it, so I'm not going to put you through a proof. But for any 3 points A, B, C on a directed line, L, then the directed distance from A to B plus the directed distance from B to C is always equal to the directed distance from A to C. It doesn't matter what order those points are in. So we're just going to get some intuition with me drawing some pictures.
Okay.
You with me so far? So the directed distance with this picture, the directed distance from A to B is this right here, positive, right? The directed distance from B to C is this right here, positive. And so from A to C, it's that whole thing. And so in this case, it's obviously true, right?
Yeah.
All right, so now let's put C in the middle. And let's try it again. The directed distance from A to B is this right here.
Yep.
The directed distance from B to C now is negative. So that cancels out this part. And so you're left with A to C. See that? Let's draw one more unintuitive case. Let's put the C over here and the A here. And just one more time. So once again, the directed distance from A to B is from here to here. The directed distance from B to C is from here back to here. So we cancel out this portion, and now we have this negative directed distance, which is equal to the directed distance from A to C.
Yeah.
In that case, it came out negative. But this was still true no matter what. You see that? And there's 3 more combinations that we could lay out to show it that I'm not going to do. I think you get it. All right, so now we have this notion of plotting points on a directed line segment. And how do we plot a point? We're going to do exactly what we talked about right here. I'm going to take my directed line, and I'm going to arbitrarily call a point on it 0, which I call my origin. Right? And then it's just like when we created a line segment, not a line segment, what did we call it before? A number line. Okay. It's just like when we created a number line from before. We started out with a directed line just like this. We randomly pick some unit, pick any length I want, doesn't matter how big of a length I pick any length I want, and now come mark that length out. Whatever that is, we're going to call that 1. Go over that length again, we're going to call that 2. Go over again, we're going to call that 3. Go backwards, go in the negative direction from our origin, we're going to call that minus 1. We're going to call that minus 2. And we're going to call that minus 3. And you've done this 100 times setting up pictures to solve math problems, right? And so now, we can associate, before we just had a line with some points on it. I had a point A right there and a point B right there or something like that. Maybe I got backwards. We had like a point A somewhere right there and a point B somewhere right there, right? And now that point A is associated with a number on the number line. And that point B is associated with a number on the number line. Which we're going to call its coordinate. So if I were to call this point here, P1, and this point here, P2, and the number it landed on here, X2, and the number it landed on here, and the number it landed on here, X1, then the coordinates of P1 are X1, and the coordinates of P2 are X2. Make sense? Okay, so that's what we're going to be saying, that's what we're going to mean with notation like this here now. So let P1 be some point with coordinate X1, and P2 be some point with coordinate X2. That's what that's saying right there. Good? Okay, so let P1 and P2 be points with these as their coordinates on a number line. Then the directed distance from P1 to P2 is always equal to the coordinate of P2 minus the coordinate of P1. We're going to prove this.
Okay.
Which will also tell us if this is the case, then this will also be the case. The absolute value of that will also equal the absolute value of that. That part's trivial. So we're just going to worry about proving this. This comes for free. Make sense? Okay, so let's prove that. So let P1, P2 be given on the number line, L, with origin at O. And I drew a picture down here when it's all said and done to help us understand what's going on. So here's O, P1 some random point on there, and P2 some other random point on there. And I forgot to say with P1 has coordinate X1 and P2 has coordinate X2. Sorry. So let P1 and P2 with their associated coordinates that we listed up there be given on the number line with origin O.
Is that how you spell origin? Yeah, I don't think so.
What did I do wrong?
I don't know.
Origin, right?
I think that's it. That looks better.
I don't know what I had before.
You had an E.
Okay, anyways. So, P1 has coordinate X1 and P2 has coordinate X2. We're assuming that. What does it mean that that's our coordinate? To say that the coordinate of P1 is X1 means that if we count out from O going over, then the number we associate with P1 is X1. So this distance right here is X1.
Yeah.
And similarly, since the coordinate we associate with P2 is X2, then the distance from our origin to P2 is X2. That's what it means to assign it that coordinate. Okay. So then our directed distance from our origin to P1 is equal to X1, and our directed distance from our origin to P2 is equal to X2. Right? Good? So then what's our directed distance from P1 to our origin? If our directed distance from our origin to P1 is equal to X1, then our directed distance from P1 to our origin is negative X1. Does that make sense? Good? All right, perfect. Then we're ready to just use this right here to finish our proof. So then the directed distance from P1 to P2 is equal to the directed distance from P1 to O plus the directed distance from O to P2. The directed distance from A to C is always equal to the directed distance from A to B plus the directed distance from B to C. You follow that? So plug in the numbers. What is the directed distance from P1 to O? That's negative X1. What is the directed distance from O to P2? That's X2. So negative X1 plus X2 or X2 minus X1. And we're done. That make sense? All right. Let's do a couple examples here and make sure you got it. So hopefully you can see this picture decently. We've got some directed number line. This is positive direction. This is negative direction. I have A, C, and B here. The coordinate of B is 2. The coordinate of C is -3. The coordinate of A is -5. So what's my directed distance from A to B? 7?
Yeah.
You positive? How do we calculate that?
2 minus -5?
2 minus -5? 7, right? So 2 minus -5 is equal to 7. And you didn't get messed up on the signs. All right, let's look at the directed distance from A to C. What's that equal to?
2.
2?
Yeah.
And how are we getting 2?
-3 subtract -5.
So you got -3 minus -5, which is 2. All right, let's look at our directed distance from C to B. What does that give us?
5.
5. We have 2 minus -3 is equal to 5. And then our directed distance from B to C, what does that give us?
-5.
-5? So that's -3 minus 2 is equal to -5. And notice that these two have to be opposites of each other. Good? Nothing weird? All right. And we'll shift over the camera. And I think we see everything we need. Okay. The author kind of did things in an ugly order, so we're going to skip ahead and come by start talking. We're going to start talking right here, and then go back once we do this column. With the exception of one thing. First, remind ourselves of the definition that we already had. We had B is less than C is logically equivalent to C minus B is positive, right? You remember that definition? Which is also the same thing as C minus B is greater than 0. Similarly, we had B greater than C was the same thing as C minus B is negative, which is the same thing as C minus B is less than 0. So that's review from things we talked about a while ago, so hopefully you don't get confused on that. So now, reminding ourselves of that fact, let's jump ahead over here and do some basic proofs, then we'll go back and look at those. So, doing some basic proofs for a second. What are we going to prove? First we're going to prove B is less than C if and only if B plus H is less than C plus H. So if we have an inequality, you can add the same things to both sides. It doesn't change the inequality. That's what we're going to prove here. With me? Okay. So this is an if and only if proof. So I need to show this being true implies this is true. And then this being true implies this is true. I have to prove it both ways. All right. So let's start by proving it this way. I'm going to show that this implies that. So let B, C, and H be real numbers such that B is less than C. Good so far? All right. So let P equal B minus C, and note that P is greater than 0. What does it mean for B to be less than C? It means that B minus C is less than C minus B. Backwards order here. But I use right order down there. Okay. So let P equal C minus B, and note that P is greater than 0. B less than C is identical to C minus B is greater than 0, by definition. We good with that? Okay. So P is equal to C minus B, and we know that P is greater than 0. So then, C plus H minus B plus H. Our question is this greater than 0? Because notice that if this minus this is greater than 0, then we just barely showed that this is greater than this. So this minus this, well, what's that equal to? Notice the h's cancel out. C plus H minus B plus H is just C minus B. H's go out. You follow that? And I know that C minus B is equal to P is greater than 0. So since p is greater than 0, then c minus p is greater than 0, so this is greater than 0. Therefore, c plus h is greater than b plus h. You follow that proof? Was there a weird part?
Makes sense.
Make sense? Make sure you're seeing everything. Because it's should be pretty simple once you see it. Okay, so what did we just really show? We just really showed that if b is less than c, then b plus h is less than c plus h. So far we showed you can add the same thing to both sides. Now we're going to show if you're here, you can subtract the same thing from both sides. So far we've shown you can add the same thing to both sides, so we're good with that one. Okay, so now I'm going to prove it this way. So now I'm going to show that if b plus h is less than c plus h, then b is less than c. So let b, c, and h in R such that b plus h is less than c plus h. Now what did I prove up here? Up here I proved you can add the same thing to both sides. Right? So if b plus h is less than c plus h, then b plus h plus some number is less than c plus h plus some number. I now know I can add the same thing to both sides of an inequality. Right?
Yeah.
And now you see what we obviously do. H plus negative h is just 0, so it's just going to give us b is less than c.
Yeah.
And we're done with that. So the proof might seem a little bit weird because we use the first part of the proof and the second part of the proof, which is perfectly legal. Anything weird on that? Do we need to go over it again? Think you got it?
Would you have to be able to do that proof with the h being the same number? Like if you did b plus h plus negative k is less than c plus h plus negative k.
I just barely proved that that's true. Here's why. Because h plus negative k is just a number. Call that number whatever you want, a. A is equal to that. I can add a to both sides.
Oh yeah.
So, still just a number. So the first part of the proof, we proved that you can add the same number to both sides of an inequality, it doesn't change it. Second part of the proof, we showed that you can subtract something from both sides of the inequality, doesn't change it. And the second part of the proof came for free from the first part of the proof, because subtracting is really just adding a negative. So that's all we did in the second part. So really, we could have just done this in one go. But nice try. Okay. So next proof we're going to do is if you have an inequality and you multiply both sides of the inequality by a positive number, it doesn't change the inequality. That's the next thing we're proving. So if R is some positive number, then B is less than C if and only if R times B is less than R times C. So if you have an inequality, you can multiply both sides by a positive number, and it doesn't change the inequality. And similarly, if you have an inequality, you can divide both sides by a positive number, and it doesn't change the inequality. That's what we're proving here. Very similar to what we just did, right? You understand what we're trying to prove? Ready to prove it? All right. So we'll start by going this way. We're going to show that B less than C implies R times B is less than R times C. So one, assume B is less than C, and we're going to let P equal B minus C. Same thing that we did above, which is greater than 0.
That doesn't make sense. C is the bigger number than B.
Did I mess up my order again? Thank you. B less than C means C minus B is greater than 0.
Okay.
And I have it messed up here again. R times C, R times B. Jeez, can't believe I made that mistake that many times. Okay, so yeah, thank you. So assume B is less than C. then that means that C, that's a minus, not times, C minus B is greater than 0, and we're going to call C minus B P, right? Okay, so P is a positive number. And we already know that a positive times a positive is positive. So then, R times P is a positive number. But R times P is equal to RC minus RB. R times P is greater than 0, and R times P is equal to RC minus RB. Therefore, RC minus RB is greater than 0, or in other words, RB is less than RC. We follow that?
Yeah.
So that would just fall from the fact that positive times positive is positive. Okay, now we're going to go the other direction, and we're going to do it similar to how we did in this proof. We're going to use the first part of the proof to prove the second part of the proof. So now we just really showed I can multiply both sides of an inequality by a positive number, and it doesn't change it. Right? So second, I'm starting with RB is less than RC. R is still a positive number, and so 1 over R is still a positive number. Right? If 2 is positive, 1/2 is positive.
Yeah.
If R is positive, 1 over R is positive. You follow that? So here I have some inequality. Sorry, I lost track of where we were. Right here. Here I have some, was it this one?
No, it's the proof above.
Proof above, up here?
It's right there.
Okay, thank you. All right, so assume RB is less than RC. And we just barely proved in the previous part of the proof, I can multiply both sides of an inequality by 1 over R, and it doesn't change the inequality. So I'll multiply both sides now by 1 over R. And the R cancels out with the 1 over R. 1 over R times R is just 1. 1 times B is just B. Similarly over here, now we just have C. So that gives me B is less than C, which is what we were after. Follow that? Okay, last thing in a nutshell, we're proving that multiplying or dividing both sides by a negative number flips the inequality sign. That's what this last proof is going to be. Not last one, second last one. So let's prove now, if R is a negative number and B is less than C, then multiplying both sides by a negative number flips the inequality sign. Furthermore, if we have some equality like this, and we divide both sides by R, which is a negative number, it flips the inequality sign. That's what we're proving. So let's start by proving this direction. Assume B is less than C. What does that mean? That means P equal to C minus B is greater than 0. Right? So P is a positive number. What's a positive times a negative?
A negative.
A negative. So then R times P is a negative number, or R times P is less than 0. Since P is greater than 0, and R is negative, R times P is less than 0. But what is P? It's C minus B. So R times P is the same thing as RC minus RB. Is less than 0. RC minus RB is less than 0 means RB is greater than RC. That's using this one right here. If C minus B is less than 0, B is greater than C. So we have RC minus RB less than 0, so this is greater than this. Follow that? Nothing weird? Okay, and now go the other direction. Assume RB is greater than RC. What did we prove in the first part of the proof? If you multiply both sides by a negative number, it flips the inequality. So I take this and I multiply both sides by a negative number, namely 1 over R. Flips the inequality. Which then gives me that. And we're done. Good? Okay? And then the last one, pretty straightforward. If B is less than C and C is less than D, then B is less than D. Or in other words, less than is transitive. It's another way you'll hear that said. Make sense what we're proving?
Yeah.
Okay. So I'm trying to show that B is, I'm going to assume B is less than C and C is less than D, and I'm going to show that that implies B is less than D. How do I show that B is less than D? I need to show that D minus B is greater than 0, right? If D minus B is greater than 0, then B is less than D. That's what it means to be less than.
Yeah.
So what is D minus B? Well, D minus B is equal to D minus C plus C minus B. We just subtracted and added a C.
Okay.
You with me? But D minus C, is that negative or positive?
Positive.
How do you know?
Because D is greater.
From right here, because C is less than D, or D is greater than C. And C minus B, is that positive or negative?
It's positive.
Positive.
It's positive from this inequality. So D minus B is equal to a positive plus a positive, which is
Positive.
positive. So we know it's greater than 0. So D minus B is greater than 0, therefore B is less than D. Sorry, I really crammed that one in there.
Yeah.
But I thought after those ones you'd be good with me just doing a lot of talking rather than writing everything. So feel like you understand those, what is that, 4 theorems? Okay, so now let's go back and say a bit more about absolute values. And we're going to do a lot more of a deep dive than the author does, because he really does a little bit of hand waving with absolute value. Okay, so let's remind ourselves of our absolute value function. Oh, let's really quick finish this now. It's something that we already noted from before, but B less than C means C minus B is positive, right? And so if I think about a directed distance from B minus, if I think about a directed distance between 2 points B and C, such that their distance is C minus B, C minus B is a directed distance for this line segment, right?
Yeah.
The directed distance from B to C is C minus B. You with me? So if C minus B is positive, then that means C is to the right of B when you plot that, or B is to the left of C. And we already mentioned that before when we talked about inequalities, but reminder again, since the author has it. Get with that? And then if L isn't directed, then this symbol, AB with the line above it, just means the length of the line segment. Like regular geometry. Okay, so that was the rest of that note. Now we're ready to go back to absolute value and remind ourselves of the absolute value function. What's the absolute value of x? It's x if x is greater than or equal to 0. It's negative x if x is less than 0. Remember this definition? We've already said quite a bit about it. Okay, so now we're going to prove a few things. We're going to prove 2 basically lemmas to get us to the main proof here. So the first thing we're going to prove is that the absolute value of C is less than or equal to the absolute value of D if and only if C is between negative D and D, where D is some positive number, or 0. It's a bit to take in, so a lot of notation. Feel like you got it? Maybe write a couple numbers really quick. Let's do D equal to 3 and C equal to 2. The absolute value of C is less than or equal to D if and only if, or 2 is less than or equal to 3 if and only if negative 2 is less than or equal to, or negative 3 is less than or equal to 2 is less than or equal to 3. Here's another way to think about it. If D is 3, what are all the values of C that will satisfy this? We're going to prove it's all the numbers C between negative 3 and 3 are the ones that will satisfy it.
Including negative 3 and 3.
Including negative 3 and 3. So as long as C is between negative 3 and 3, then the absolute value of C will be less than or equal to the absolute value of D. for the special case where d is equal to 3. And we're showing this where d is equal to any number greater than or equal to 0. Follow that? And this is a very useful little lemma to have. When you have an inequality with absolute values that's oftentimes hard to use, you can rewrite it this way and get rid of your absolute values.
What is a lemma?
A lemma, it's a helper proof. So it's something that you're proving, but not necessarily for its own sake, but just to help you with a future proof. But really, whether you call something a lemma or a theorem, there's no hard, fast rule. A lemma is a theorem, and a corollary is also a theorem. A corollary is something that we say kind of immediately follows from the theorem we just proved. So lemmas are usually viewed as helpers. Corollaries are usually viewed as obvious from the theorem we just proved. But they're all theorems. Okay. Anyways, so now that we got some intuition for this, let's prove it. This is an if and only if proof, so I need to prove that if the absolute value of c is less than or equal to the absolute value of d, then we have this right here. So I'm going to prove it this way first. So let c and d be real numbers such that the absolute value of c is less than or equal to the absolute value of d, and we're always going to require d is greater than or equal to 0. So I'm showing that this implies this. With me? Okay, I'm going to break this up into two cases. For c, we can have c is greater than or equal to 0, or we can have c is less than 0, and those are the only possible cases for c. I'm going to show that when c is greater than or equal to 0, we get this, and I'm going to show that when c is less than 0, we still get this. Therefore, no matter what c is, if this is true, this is true.
Okay.
That's the big picture of what I'm going to do here. Okay. So let's get started. So if c is greater than or equal to 0, what's the absolute value of c if c is greater than or equal to 0?
C.
It's just c. Since c is 0 or a positive number, its absolute value is just itself. What's the absolute value of 2?
2.
What's the absolute value of 25? What's the absolute value of 0?
0.
0. So as long as the number I ask you about is greater than or equal to 0, its absolute value is just itself. That make sense? All right. So if c is greater than or equal to 0, then the absolute value of c less than or equal to the absolute value of d can be rewritten as c is less than or equal to d. Because the absolute value of c is just c, and the absolute value of d is just d. How do I know that the absolute value of d is just d?
Because d is a positive number.
Right there. D is greater than or equal to 0. With me? So this inequality is the exact same as this inequality for this special case.
Yeah.
Okay. So if c, I know c is greater than or equal to 0, and I know c is less than or equal to d, therefore I know that c is greater than or equal to 0, and c is less than or equal to d.
Okay.
Pretty obvious? Okay. And then, if c is greater than or equal to 0, c is definitely greater than or equal to any negative number. And so we got negative d is less than or equal to c is less than or equal to d. And we're done for this case. For the case where c is greater than or equal to 0, we show negative d is less than or equal to c is less than or equal to d. Now let's do it for the case where c is less than 0. Ready?
Yeah.
Alright, so if c is less than 0, then what's the absolute value of c now? If c is less than 0, what's the absolute value of c?
Negative c.
Negative c. So the absolute value of c is now negative c. The absolute value of d is still just d. Follow that? Okay. Now I'm going to multiply both sides of this inequality by negative 1. What's that going to do to the inequality? It's going to flip the sign. So if I multiply both sides of this by negative 1, now it's like this. Negative d is less than or equal to c. Good? All right. So now if negative d is less than or equal to c, and I know that c is less than 0, then I know negative d is less than or equal to c, and c is less than or equal to 0. If it's less than 0, it's definitely less than or equal to 0, right?
Yeah.
And then finally, if c is less than or equal to 0, c is definitely less than or equal to some positive number. D. So therefore, shouldn't have looked away, lost it, we're right here. So we just barely showed that negative d is less than or equal to c is less than or equal to d. So we're done with this direction. We just barely showed no matter what value c is, as long as the absolute value of c is less than or equal to the absolute value of d, then negative d is less than or equal to c is less than or equal to d, where d is greater than or equal to 0. Now I'm going to show, as long as d is greater than or equal to 0, if this is true, then this is true. So that's going to be this direction. So we're going this way now. So let c, d, and r such that negative d is less than or equal to c is less than or equal to d, where d is greater than or equal to 0. And now I'm trying to show this statement holds from this statement. I'm going to use this to show it implies this. Right? Okay. We were right here. Once again, we have two cases for c. Either c is greater than or equal to 0, or it's not. Right? So we're going to break up into those two cases and show that in either one of those cases, we get this. So, first case, we'll assume c is greater than or equal to 0. So if c is greater than or equal to 0, then c less than or equal to d, notice I know that from here. I'm just taking this information and putting it right there. I know negative d is less than or equal to c is less than or equal to d, so I definitely know c is less than or equal to d, right? And c can now be rewritten as the absolute value of c, and d can be rewritten as the absolute value of d. Because the absolute value of c is c, where c is greater than or equal to 0. And the absolute value of d is just d, since d is always greater than or equal to 0. Follow that one? Okay, so now what about if c is less than 0? Well, if it's a negative number. So if c is less than 0, then we're going to take this part of the inequality. I know negative d is less than or equal to c, so negative d is still less than or equal to c, right? So negative d is less than or equal to c. Multiply both sides by a negative number, by negative 1, and we get negative c is less than or equal to d. Right? And now, negative c, that's the same thing as the absolute value of c. Since c is now less than 0. If c is less than 0, then the absolute value of c is negative c. And the absolute value of d is still just d. So we just rewrote that like that. And so once again, we get the absolute value of c is less than or equal to d. Therefore, the absolute value of c is less than or equal to d if and only if negative d is less than or equal to c is less than or equal to d, as long as d was a number greater than or equal to 0. Bit of a mouthful of a proof, probably the hardest thing we've got today. So if you understand that, I think we're pretty good. Any questions on that one? All right. So now we'll prove a quick little lemma before we get to the main event. What's our quick little lemma? Negative the absolute value of x is less than or equal to x is less than or equal to just the absolute value of x. And it's pretty obvious, right? Negative the absolute value of negative 3 is less than or equal to negative 3 is less than or equal to the absolute value of negative 3 when we plug in a negative number. So we get negative 3 is less than or equal to negative 3 is less than or equal to 3. Right? So this was plugging in negative 3 for x.
Yeah.
And now notice what happens if I plug in just 3 for x. Good intuition for what we're proving? Okay. So there's the intuition for what we're proving. Let's prove it. So I'm proving this statement. We're going to break it up into two cases. The case where x is greater than or equal to 0, and then the case where x is less than 0. And very common, you break your proofs up. When you're doing proofs with absolute value, it's very common that you break them up in these two scenarios, because then you know what the absolute value is. I can't figure out what the absolute value of x is until I know whether or not x is greater than or equal to 0 or less than 0, which is why that's pretty standard for all these proofs I'm doing with absolute values.
Yeah.
Okay, so let's take our first case. If x is greater than or equal to 0, then what's the absolute value of x?
Just x.
Just x. Oh, sorry. We'll make the substitution right here. But first, let's see something that's trivially true. So if x is greater than or equal to 0, then negative x is definitely less than or equal to x, right? And x is equal to itself, so x is less than or equal to itself. Okay, So now going from here to here, I'm going to do my substitution with absolute values. Negative x is the same thing as negative absolute value of x, and x is the same thing as absolute value of x. So I got negative absolute value of x is less than or equal to x is less than or equal to absolute value of x. Good? Okay, so let's do it the other way. Now let's say that x is less than 0. If I know that x is less than 0, then x is less than or equal to negative x. If x is a negative number, then x is less than or equal to negative x. If x is negative, negative x is positive. So a positive is greater than or equal to a negative if x is negative. You see that? Hopefully you see that. Students usually get pretty scared when they see something like x is less than or equal to negative x. Usually throws them for a loop. That's true where x is a negative number. Okay? So here we have x is less than 0, or in other words, x is a negative number. Therefore, x is less than or equal to negative x, is how we're getting this part. And x less than or equal to x is trivially true, because x is equal to x. So it's this part that you need to wrap your head around. Once you got that, you're good to go. We got this? Okay. So now, notice that x is the same thing as negative negative x, right? This we replace with that. This x we kept just x, and this negative x we kept just negative x. Right? And now, notice that if x is less than 0, what's the absolute value of x?
Negative x.
Negative x. So I can replace that negative x with absolute value of x, and I can replace that negative x with absolute value of x. And we get negative absolute value of x is less than or equal to x is less than or equal to absolute value of x. And we proved it. Any questions on that one? Think you got it?
Yeah.
Okay. So now we're going to combine these two together to one of the more famous statements in mathematics, one of the more famous theorems, has a special name. It's called the, you remember it? From real analysis?
For some reason, I think it has triangle in the name.
It's called the triangle inequality. And this is it in one dimension, the Pythagorean, not the Pythagorean theorem, but we'll see a notion of it in 2 dimensions as well. It's a common, similar type of statement. It shows up in a lot of fields of mathematics, and we also saw it in topology. Anyways, so let's go over it now. What are we proving for this special version of the triangle inequality? We're showing that the absolute value of a sum is less than or equal to the sum of the absolute values. The absolute value of a sum is less than or equal to the sum of the absolute values. Good? Alright, so let's prove that. So let x1 and x2 be any 2 real numbers, and observe that, using the lemma down here, negative the absolute value of x1 is less than or equal to x1 is less than or equal to the absolute value of x1, and negative the absolute value of x2 is less than or equal to x2 is less than or equal to the absolute value of x2. So we just barely use this lemma twice. Good? Now I'm going to construct an inequality adding these two together. So I know that this is less than or equal to this, and I know that this is less than or equal to this. Therefore, this plus this is less than or equal to this plus this. So this plus this is less than or equal to this plus this, which is less than or equal to this plus this. You with me?
Yeah.
Okay, so you're good with this statement. Now I'm just going to put on some random parentheses. So rather than writing this as negative absolute value of x1 minus absolute value of x2, I'm going to write that negative absolute value of x1 plus absolute value of x2. Yep. So we have negative some number is less than or equal to x1 plus x2 is less than or equal to that same number again. Notice that and that are the same number. So I have negative some number less than or equal to x1 plus x2 is less than or equal to some number. Now, what do we know about this number? Do we know anything about that number?
Positive?
It's positive. Can an absolute value ever spit out a negative number?
It cannot.
It cannot. Okay. So that's positive, positive plus positive is positive. So this is a positive number. Right? So I have negative some positive number, less than or equal to x1 plus x2, less than or equal to some positive number. Notice this statement right here. Negative some positive number, less than or equal to something, less than or equal to some positive number, means this is true. I can go from this to this. So, I can go from the absolute value of my middle term, the absolute value of c, is less than or equal to d.
The absolute value of d.
The absolute value of d, which can also just be d. I don't know why I have an absolute value there, because d is greater than or equal to 0. So the absolute value of d is just d. Takes a bit to see it, but this right here is your d, and that's your c. So we have absolute value of c is less than or equal to d. Wonderful. Okay, so that's our triangle inequality. And that's probably the biggest thing to come out of this chapter.
Why is that useful?
The triangle inequality, it gives us a way of, it's like the one-dimensional version of, let's see where I get this name. And it's like the one-dimensional version of this. Pick any triangle you want in geometry. Call the points A, B, and C. The original way that the triangle inequality was proved was in a two-dimensional case, and it was proving that the distance from A to C is always less than the distance from A to B plus the distance from B to C.
What?
The distance from A to C is always less than or equal to the distance from A to B plus the distance from B to C. It's correct. If you have to walk remember geometry, these aren't directed distances, regular geometry. If you have to walk somewhere, it is always faster to walk directly there than to walk to some other point and then walk to your destination.
Combined point. Yeah. Okay.
Yeah, duh. It's pretty obvious, right? And that's true for no matter what kind of triangle you draw. Doesn't matter how crazy you get with your triangles. The distance from here to here is always less than or equal to the distance from here to here plus the distance from here to here.
Equal to?
Less than or equal to.
That would be a line.
In this case, it's always going to be less than. Unless you're going to have some weird definition of triangle that makes a line a triangle. But it shows up in a lot of cases. So that's like the Euclidean version of the triangle inequality.
Okay.
But the similar notion shows up a lot in geometry, or in different fields of mathematics. It's basically the same theorem in a bunch of different fields. It's called the triangle inequality because the first place it showed up was Euclidean geometry. And so even though this has nothing to do with triangles, it's still named the triangle inequality. Because it's talking about a similar thing. Okay, so now let's move to talking about graphs of equations, or graphs of solutions to equations, or graphs of numerical statements. So, what does it mean to graph something? So, let's make sense of that really quick. The graph, and so far we're just talking about in one dimension, we'll talk about in two dimensions later. The graph in one dimension of a single variable numerical statement. So a numerical statement which only has one variable in it, like x, is the set of points on the number scale representing the solution set. So if your numerical statement has some solution set, find their corresponding points on the number scale. This line, this number line, I don't know why I call it number scale. We're just calling it number line. I'll just call it number line. Find its corresponding points on the number line. In other words, plot all the coordinates of that solution set, and that's what we mean to graph it. Pretty straightforward, and you already have this notion of graphing in your mind. So, quick example. If I say x is less than 3, what is the solution set here? What are all the numbers x that satisfy this?
Every number less than 3.
Everything below 3. So if we went and I drew in all the points on the real number line, less than 3, I'd be drawing in all these points, not including 3. And to say that we're not including 3, we put an open circle there. If this were less than or equal to 3, I'd put a closed circle there and I'd fill that in. Make good sense? Pretty straightforward? Let's go back to a problem that we did before that you guys got really stuck on. So we had 2x squared minus x is equal to 1, and your job was to find the solutions to this.
Yeah.
Right? And obviously, first thing we do is put all the numbers on the same side, equal to 0.
Yeah.
And then we factor it, so we got 2x plus 1 and x minus 1 is equal to 0. And so what are the values of x that make this true?
1 and 1/2.
Negative 1/2
Negative
and 1.
1/2.
So negative 1/2 and 1 are the two solutions, plot those points. So here is the graph of the solution to this expression. Good? Alright. Let's let you try one. So we have x is equal to 3 and x is less than 2. Which points do I plot?
All the numbers less than 2, not including 2.
All the numbers less than 2, not including 2.
And then a point at 3.
And then a point at 3. Like that, right? Right? Anything weird about that?
Wait.
There's a lot weird about that. There are no numbers that are 3 and less than 2.
That would be correct if it was.
That would be correct if this were an OR. But that wasn't an OR, that was an AND. So there were no solutions. Okay? Now let's try another one. Let's look at the numbers. X such that 2 is less than x and x is less than 5. That's what we mean here. We mean this. There's the shorthand for that. So we have 0, 1, 2, 3, 4, 5. Here's our 2, here's our 5. What are we drawing? 3, 4, 5? 3 through 4?
I'm thinking this wrong.
So you're saying include 4 as a point, and everything over to 3?
Yeah.
Do I include 3?
Yes.
Okay, so it's this segment. 3 to 4?
Oh, no.
No.
Yeah, okay.
All right.
Add circles on two sides.
Open circle on 2.
Open circle on 2.
That's 30.
Open circle on 2.
Point to the negative.
Huh?
Point to the negative.
Going this way?
I think so.
Over here? And then what else? Is that it?
Open circle on 5.
Open circle at 5? And those are all the points between 2 and 5?
I don't know.
We want, don't guess, read. 2 is less than x, and x is less than 5. Those are the points we're looking for. Pick one of the points you named, 0. Is 0 greater than 2 and less than 5? No. So 0 definitely isn't included.
So an open circle around 0.
All right, so let's start again. Open circle on 0. 0, 1, 2, 3, 4, 5, 6. All right, what am I doing?
Open circle on 2, open circle on 5, connect.
Open circle on 2, open circle on 5. Connect them?
Yes.
Yes. Those are all the points between 2 and 5. If x is greater than 2 and x is less than 5, that means x is between 2 and 5. Those are all the points between 2 and 5. Good? Okay, and then we already proved that column over there, so that's the end of the whiteboard, unless you have any more questions on the whiteboard. The green whiteboard. The green blackboard. All sorts of wrong words. All right. So let's move over now to the whiteboard. And see if I can get this all in one go. All right. We're cutting off a little bit over there, so have to remember to adjust it. Okay. So now with everything we learned, let's solve some inequalities. So let's solve 7x over 3 minus 1 is less than 17 minus 2x over 3. We're looking for all the solutions to that thing. How are we going to find them?
Add 1 to both sides.
Add 1 to both sides?
Yeah.
What does that do to my inequality?
Stays the same.
Nothing. It stays the same. That was the proof here. If you have an inequality, you can add the same thing to both sides. Doesn't change the inequality. So if we add 1 to both sides, then we're going to get 7x over 3 is less than 18 minus 2x over 3, right? I added 1 to both sides.
Can multiply by 3.
Multiply both sides by 3. Okay. So that's also the same as, put back and forth arrow there to minus, it's logically equivalent to, multiply both sides by 3, and we're going to get 7x. What's that going to do to my inequality?
Nothing.
Keep it the same.
Keep it the same. When we multiply by a positive number, it doesn't change the inequality. If b is less than c, then r times b is less than r times c, as long as r was a positive number. 3 is positive. So we get 7x is less than, what's that equal to?
54 minus 2x.
54, thank you.
Yeah.
Minus 2x. Okay, now what?
Add 2x.
Oh wait,
9x.
x might be negative.
Yeah, x might be negative. So can we just add 2x to both sides?
Yeah.
Yeah, we can.
Yeah, because it's still just a number.
Mhm.
And we can add the same number to both sides. So add 2x to both sides and we get 9x is less than 54, right?
Mhm.
Now what can we do?
Divide by 9.
Divide by 9, and what does that give us?
X is less than 6.
Right?
Yeah.
And now, just check really quick to make sure you didn't screw anything up in case you're worried. Let's pick some number like 3 will be a nice one.
Yep.
Pick some number 3, plug it in here. What do we get when we plug in 3? We get 7 minus 1 is less than 17 minus 2. Is that true?
Mm-hmm.
So 3 works. And if you were told to also graph your solutions, what would that look like? Here's 0, here's 6. What do I do?
Open circle at 6 going left.
Open circle at 6 going left. All the values less than 6.
Yep.
Good?
Yeah.
Okay. Now say that you were given a bit more challenging problem, and you were told to prove that if x is not equal to 1 and x is greater than 0, then 1 over x plus x is greater than 2.
Okay.
Yeah, what? That's a tough one, right? How do we do a proof like that? Well, you might come up with the first line of the proof. Let x be a real number such that x is not equal to 1 and x is greater than 0. Okay, that's easy. Now notice the next thing I do. I say, look at this. X minus 1 squared is greater than 0. Square that out. Hold on. Is this always true? First off, let's notice if this is always true.
Because you're multiplying.
A number squared is always positive unless it's 0. Can this ever be 0?
No.
No, because x can't be 1. So this can't be 0. Okay. So this is always a positive number, right? So square that out. X squared minus 2x plus 1 is also going to be greater than 0. I just multiplied it out.
Mhm.
Add 2x to both sides. And then since x is positive, I know x is positive because it's greater than 0. Since x is positive, when I divide both sides by x, I get this. So I proved it. But notice that my last line of my proof is kind of like what we were given to start with. How on earth did I know to start with this?
You worked backwards?
Yes. So the part that you don't see here is how I actually solved the problem. And then I just wrote the proof. And so here's how you would have really solved this problem. You do what we call scratch work for the proof. So you would have started out by writing this thing. You would have come and written 1 over x plus x is greater than 2. And then first thing you would have said is I want to multiply both sides by x, right?
Mm-hmm.
Now you know that x is going to be greater than 0, so that doesn't change your inequality here. So multiply both sides by x, and I would have gotten, 1 plus x squared is greater than 2x, right?
Mm-hmm.
Subtract 2x from both sides, and we get 1 plus x squared minus 2x is greater than 0. We can rewrite that if it helps you think about it. X squared minus 2x plus 1 is greater than 0. And then that's the same thing as x minus 1 squared is greater than 0.
Yeah.
And then so this one is obviously true given our conditions of x. So you'll notice that I started with this and then worked backwards to this in my proof. Which is very common how you prove those. Kind of like proving what a limit was in calculus. That type of thinking. Okay, so that's how you do stuff like that. Alright, sets. Some simple stuff with sets. We won't be doing a ton with sets in this class, but we'll be doing enough that it's good for you to know the basics of sets in the class and the basic operations on sets. So, how many of you have never seen union before? You're a liar, you might not be. We did sets in calculus a lot.
I don't think you.
But you don't remember it, I guess. Well, I'll go find the textbook. We'll bring it to physics. Alright, so A union B, we define that to be the set of all x such that x is in A or x is in B. Let's do an example of that really quick before we move on. So let's say that A is equal to the set 1, 2, 3, and B is equal to the set 4, 5, 6, but I want this to be 3, 4, 5. Okay. So A is equal to the set 1, 2, 3, B is equal to the set 3, 4, 5. What is A union B? What are all the things that are in A or B? 1, 2, 3, 4, 5. That's everything that was in A or B. Make sense?
Why not A and B? Would that make sense too? Saying it that way.
Next, define intersection. What's A intersected B? That is a set of all x such that x is in A and x is in B. Okay? So let's write that one out. A intersect B. What are all the things that are in A and B?
3.
Just 3.
Oh.
That's the only thing in A and B. 1 is not in B. So it's not in A and B. Perfect. Alright, and then we have a notion of a set difference. What's a set A minus B? That's a set of all x such that x is in A and x is not in B. If x is in A and it's not in B, then it's in A minus B.
Yeah. Okay.
Everything in A that's not in B. Alright, so let's write that out. What's A minus B?
1, 2.
1, 2. No, 4, 5.
Oh, yeah, B.
It's everything in A that's not in B. We start with A, and then we get rid of everything that was also in B. Perfect. Alright, and then just make sure you got it. Let's do 3 more again. This time we're going to be working with A and C. And C is just a set containing 7. Alright, so what's A union C?
1, 2, 3, 7.
1, 2, 3, 7. what's A intersect C?
The empty set.
Nothing. Or the empty set. Which, remember, we use that symbol for the empty set.
Yeah.
So A and C have nothing in common, right? So, definition. Two sets A and B are called mutually exclusive, provided that their intersection is the empty set, or they have nothing in common. That's what it means for two sets to be mutually exclusive. Make sense? And then finally, what's A minus C? 1, 2, 3. Or in other words, it's just A again. Good? Okay? Draw a Venn diagram really quick here to help you get a picture of these. So here, this circle right here, well, that shape, not a circle, is A, and this right here is set B. With me? So everything in this right here is A minus B. Just this portion is A minus B. It's everything in A that's not in B. This piece right here is the intersection of A and B. Everything that's in both A and B. This thing right here is B minus A. And then the whole thing together is A union B. Make sense? Wonderful. Move the camera a little bit more for this last part. Okay, some properties on sets. If I take A and I union it with itself, what do I get? Just A. The set unioned with itself is just that set. If I take a set and I intersect it with itself, what do I get?
Just A.
Just that set. Okay, if I take A and I union it with the empty set, what do I get?
Just A.
Just A or the empty set? A? Alright. If I take A and I intersect it with the empty set, what do I get? The empty set? Or A again?
The empty set.
Huh?
The empty set.
The empty set. Okay? If I know that... Oh, no, sorry. Furthermore, just something we know, A intersect B is always a, remember this symbol? Subset. A intersect B is always a subset of A. It means, being a subset means it's contained in. So A intersect B here is just a portion of A. It's a subset of A. Or A intersect B here is just a subset of A. And then last thing, if I know that A is a subset of B, then A union B is just equal to B. So let's draw a picture of that really quick. Here's B. If I know that A is a subset of B, then what's A union B? Just B. Make sense? Good. All right. A lot more properties. A union B is the same thing as B union A. Or in other words, union is?
Associative or commutative?
Commutative. A union B is the same thing as B union A. Or in other words, union is commutative. A intersect B is the same thing as B intersect A. Or in other words, intersection is also commutative. A union B union C is the same thing as A union B union C. Or in other words, union is associative. And A intersect B intersect C is the same thing as A intersect B intersect C. Or in other words, intersection is associative. So those ones are pretty obvious. Here's the interesting ones, our distributive properties for these. A intersect B union C is the same thing as A intersect B union A intersect C. Now that one's a bit harder. So let's color this out in our Venn diagram and make sense of it. We were looking at this one, right? Alright, so first off, B union C, let's look at that. B union C, that's right here. These two, right?
Yep.
And I want where that intersects A. Where that intersects A, that's going to be this, this, and this. So that is this set right here. Everyone see that?
Yep.
Now let's look at this. We have A intersect B. A intersect B, that's these two sections. Oh, sorry. Oh, keep looking down and then up. Alright, looking at this one. Alright, A intersect B, that's these two sections. A intersect C, that's these two sections. So these two sections union these two sections are those three sections.
Yeah.
And so that's this one. We see that?
Yep.
Alright, now let's make this one make sense. So, erase those. Okay, so now A union B intersects C. So first off, B intersects C is this right here. Right? And then we're unioning that with A. A union B intersects C. So union that with A, we have all of A. All those sections, right? Okay, and we're saying that's the same thing as A union B, so everything in here, in this whole circle and this whole circle, A union B are both these circles intersected with both these circles.
Yeah.
Take both these circles and intersect it with everything in both these circles. So both of them had all of A, so all of A shows up in the final expression. But where do these two overlap? Just right there. You see it? Good? No? Yeah? Okay. So those are the weird ones. And then the last one's pretty obvious. If A is a subset of B and B is a subset of C, then
A is a subset of C.
there you go. A is a subset of C. Or in other words, subsets are commutative. Transitive. Thank you. Commutative. Transitive property. Yes. Okay. And then last thing that we go over is just solving some inequalities. So need some space, but space that's on the camera. You can definitely see this far. So at the very end of the chapter, he goes back and reintroduces us to solving some more complicated inequalities. And so we'll just go over how to solve them. I'll just show you. I'm not sure what to call it. Combinations of inequalities, something like that. So how to solve something like 4 minus x is less than 3x minus 2 is less than or equal to x plus 8. Okay, so how do we solve a system of inequalities like this? And our job is to solve this. First off, what does it mean to solve?
Find x.
Find all the x's that satisfy that expression. Find the set of all values that satisfy that expression when we plug them in for x. Okay, so what are we looking for? We're looking for all the x's that satisfy this, so we want x to satisfy 4 minus x is less than 3x minus 2, and we want 3x minus 2 is less than or equal to x plus 8. So we want to find all the places where this is true, and all the places where this is true. So we'll find the solution set to this, we'll find the solution set to this. Since we want the x's to be satisfied this and this, we take the intersection of those solution sets. We want all the x's that are in here and in here.
Okay.
Does that make sense? So that's basically as much as we're really going to be using set theory for a lot of this. Simple cases like that. Intersecting two solution sets together. So, and then when we split it up like this, now we know how to solve these. We already did ones like that, but let's just do it. Tell me what to do.
Add x to both sides.
Add x to both sides. So we got 4 is less than 4x minus 2. We added the same number to both sides. Doesn't flip our inequality.
Yep.
Now what?
Add 2 to both sides.
Add 2 to both sides. Again, adding a number to both sides doesn't change our inequality. Now what? Divide by 4. Once again, doesn't change our inequalities. So we get 3/2 is less than x. 6/4 is the same as 3/2.
Yep.
So I got x is greater than 3/2. Let's look at this. Tell me what to do.
Minus
Both
x.
sides.
Minus x to both sides. So we get 2x minus 2 is less than or equal to 8.
Then add 2.
Add 2. 2x is less than or equal to 10.
Then divide by 2.
Then divide by 2. And we get x is less than or equal to 5. Thank you. Now, plot this solution. Probably overkill. You guys probably already get it, but we'll do it anyways. 1, 2, 3, 4, 5. Minus 1, minus 2. Okay, so I'll start by plotting this solution. X is greater than 3/2. Where is that true?
Circle 3/2.
So at 3/2, which is right here, put a circle. I'm not going to draw on the number line. I'm going to draw above it, so we can draw both of them. And then what?
And then x is greater than, so to the right.
So then to the right. So everything here satisfies this expression, right? All right, what about this expression? How do we do that one?
Close circle at 5 and then to the left.
Close circle at 5, and then to the left, like that, right? Now we want all the places that satisfy this and this, or in other words, we're taking the intersection of this set and this set. And when I intersect this set with this set, I'm left with an open circle here, I'm left with a closed circle at 5, and all the points in between, like that. Or represent with set builder notation, our solution set is a set of all x such that 3/2 is less than x is less than or equal to 5. Same thing. Right?
Yep.
Okay. Let's do one more to use some of the stuff we learned about previously. So one more example, and then we're done for today. So the last example is solve the absolute value of x plus 1. Make my absolute value sign big so we don't get confused with the 1. Is less than 3. All right, how do we even start with that thing?
The theorem that we did over there, the third column, the middle one.
She's talking about this one. If you have the absolute value of something is less than a positive number, the negative of that positive number is less than or equal to c is less than or equal to the positive number. So I have something is less than. If it's less than, it's definitely less than or equal to. Right? And so this is the same thing using that theorem as negative 3 is less than x plus 1 is less than 3. And that's why that little theorem right there is so useful. We don't really know how to deal with inequality or absolute values, but splitting it into two inequalities, that's easy. Right? Now, we don't have to split up these inequalities if you don't want, like we did in the other problem. You can work with it like this if you want. All in one go. You don't need to split this up into two. Just remember to keep track of what your inequalities are doing. Right?
Yeah.
So I'm going to solve it kind of stupid, but just to show you how we keep track of our inequalities. So the first thing I'm going to do, for some crazy reason, is I'm going to multiply this thing through by negative 1. Why? Why not? So negative 3 times negative 1, that gives me 3. Now we flip our inequality sign since I multiply by negative 1, and we get negative x minus 1 is greater than negative 3, right?
Okay.
And that's what I would have done if I would have multiplied by negative 1. Stupid thing to do, so we're going to backtrack now. But just keep track of, as long as I'm manipulating all three the exact same way, just flip your inequalities together. But I don't think we're going to have to flip the inequalities when we actually solve this. Okay, so what's the first thing I actually want to do for real now? Huh?
Minus 1.
Minus 1. So minus 1 from all three sides. All three sides. And so we get negative 4 is less than x is less than 2. And that's our solution. Our solution is a set of all x such that negative 4 is less than x is less than 2. Or if we were told to graph our solution, we'd come over here, we plot negative 4, and we plot 2, and we do open circle, line over, open circle. So it's actually a lot quicker not to split this up as two inequalities. So you don't have to. You could have. We've got the same thing. All right, and that's that. That finishes off chapter 2, and now we're into chapter 3, which will be going back to the Cartesian coordinate plane. Any questions about anything we talked about today? Good. And we should be good to continue class next week as normal, right?
Let's see why not.
All right. Well, then I'll see you next week.